Okay, so this is part one of this video to talk about some key concepts in statistics. So from a topics perspective, the generic topic I'm talking about, the technical term is called sampling distributions. The main idea behind sampling distributions comes from this idea that very often we collect data, right? But we're not able to collect data on every single person of interest, right? So normally we get a random sample. So the idea with a random sample is, well, each time you collect a random sample, right, each random sample will vary from one another. So how do we measure this variation from random sample to random sample? So that's basically what sampling distributions are about, and I'll tie it in with some more concrete examples. So as I said, we will cover a few concepts in statistical theory, and the main idea is we want to assess how we can use the data from our sample to make inferences about the larger population of interest, right? So, right, if we've sampled 500 people, right, and based on those characteristics of the 500 people, can we then maybe extend those conclusions, right, to the American population, for example? So the first things first, we'll kind of look at some basic ideas that you might have seen before, but we kind of use those ideas to tie in with a lot of the things that we'll talk about next. So very often what we do is we like to summarize our data, right? After we collect our data, we want to summarize it. So in this example, the data are about heights of 400 teenage girls in the United States, right? So out of the 400 girls, 32 of them have a height between 58 and 60 inches tall. 44 of them have a height between 60 and 62 inches. So with quantitative data, right, so height is quantitative, right, because it's a numerical value where arithmetic operations make sense. We typically represent this with a histogram, right? So one way to summarize it is through a histogram. So histogram kind of looks like this, where right, the height kind of gives us the number of girls, right, in that particular range, right? So in the 64 to 66 range, right, we have 92 such girls over there, right? So this rectangle over here, right, represents the height between 64 and 66 inches, and 96 of them have that height. So that's how we read a histogram, right? The vertical axis represents the numbers that we see for that particular range. So but that's not the only thing we can see, right, with this particular histogram. We can kind of say it looks symmetric, right, because if you view this around 65 as the midpoint, right, this looks like a symmetric graph, right? Symmetry means that it's like a mirror image, right, where if you put the mirror at 65, we also see, right, that the number of girls that have heights that are further away from the middle get lesser and lesser, right? So that's what we can kind of see with this particular histogram, right? So we say we have an idea of the center of the data, right? We say about 65. Variability of the data, right? So if you go back, it's about between 58 and 72 inches tall. And distribution of the data. So what is the distribution? So the distribution basically informs us about the possible values of the heights, right, which was between 58 and 72, as well as how often various values occur in our data, right? That's basically what our histogram is telling us. So the distribution is usually a description of the shape of the histogram. What kind of information can you glean from the histogram? Right, so as I said, the distribution of this data for this histogram, right, most common heights around 64 to 66 inches, heights are between 58 to 72. As heights are further away from 65 inches, or further away from the center, they become less likely to occur. So these statements all describe the distribution of this particular histogram, right, of our data. Now let's take a look at this example, right? So let's have this question, right? Based only on this histogram. So earlier on, right, I did give you a table, right, of the number of girls in each of these. But let's say you don't have that table. Now, what are some ways in which you can estimate the proportion of girls who are at least 68 inches tall? Right, so based only on this histogram, how would you estimate the proportion of girls who are at least 68 inches tall? So there are probably a few ideas that you might have, right? You could just say, hey, let me just read off, right, the value on the y-axis to add up, and then add up all these heights, right? And that all those heights will give me the sample size, the total number of girls, and then I'll just add up the heights for this bar over this rectangle here and the height for that rectangle over there. Right, so I'll take this height plus that height divided by all of these heights, and that will give me the proportion. So that's probably the most obvious way that you probably thought about. Another way to think about that is, well, I could, instead of using the height, I could use, since the width, right, of all of these rectangles are the same, so instead of just using the height, I could use the areas associated with each of these rectangles, right? Because area is, right, so if you recall, right, area is equal to height times width, right? But the width is constant for all of these rectangles, right? So if you're adding up all the heights and then, right, if you're using the heights to estimate a proportion, well, we could use the area as well because, right, it's just a constant multiplied with the height. So I could find this area, right? If I want at least 68 inches tall, means I need this area here and I need this area here, right? So I take this area plus that smaller area, and then maybe I divide it by, right, all of these, the areas of all of these all these shapes, all these rectangles. Yeah, these are all rectangles, right? So add up all of these 7 rectangles, right, their areas over there, and that will give me the proportion 1 2 3 4 5 6 1 2 3 4 5 6. There's just one more, right? So this will give me a proportion. So the main idea is that we could use areas, right, under the histogram, associated with the histogram, to find corresponding proportions, and we'll be applying this idea a lot throughout this class. Right, so you might say with this example, this kind of looks like a long way of doing it, and I can kind of see why you feel that way. But later on, we'll see why it's easier using areas under some other circumstances. So for this particular circumstance, maybe not the most obvious, but I'm trying to tie in, right, why this idea of area can be used to express proportions. Right, so I did say, right, we could find area under each of these rectangles. Well, another thing could do is, well, could we actually find a mathematical function, right, that approximates this histogram? So maybe I'm able to find a function that's a curve, maybe, that looks like this, and then use the area under the function to estimate the proportion, right? So, right, area under the mathematical function. So let me call this mathematical function f of x. Right, and I want greater than 68. So maybe I could shade all these areas over here. Right, so I could shade all these areas over here. Right, so this shaded area divided by, right, the entire shaded area under the curve, right? So I could find the proportion as that little bit that I shaded divided by the area under the whole curve, right, and that would give me the proportion that are right, that's at least 68 inches tall. Right, so the way we go about doing this, right, is that we can simply then take an integral, right? So if you recall from your high school days, right, an integral of this mathematical function from 68 all the way to the maximum value, which is until infinity, right? So that is one way in which we could consider, right? So this is how we might evaluate this numerator of this proportion, right? And then divide it by the entire area, right, from negative infinity to infinity. So that's the main thing that we're working with. So what we're going to do is we're going to define what we call a probability density function, right? So these mathematical functions are called probability density functions. So what I showed in the previous slide isn't quite accurately a probability density function. A probability density function has this additional property here, right? So there are these two properties, non-negative, and they must integrate to 1. So it's basically a scaled version of the previous curve I drew, right? So the previous curve I drew, we're going to scale it in such a way that the entire area is 1, right? So the reason for that is if I make the entire area integrate to 1, then, right, that probability that I wanted to find, right, of at least 68 inches tall is simply just integrating the mathematical function, the probability density function, from 68 all the way to infinity. Now, I don't have to divide by anything because the total area is 1, right? So dividing by 1, I don't have to do much with that. So that's what we're looking at, right? So what are some common probability density functions that we'll look at? We'll be looking at the probability density functions associated with the normal distribution. T-distribution can be viewed as very similar to the normal distribution. So I'll be focusing on the normal distribution a lot more. T-distribution is very, very similar. Chi-square distribution, F distributions. So let's take a look at the normal distribution, which is the one, as I said, that we will look at the most. So a normal distribution is a symmetric bell-shaped distribution. So if you think about bell-shaped and symmetric, right, we basically say it's a shape that looks like this, which matches with our previous histogram. So a normal distribution is always specified with its mean and standard deviation, right? So the mean denotes the center of the bell shape, and the standard deviation describes the spread, right, of your normal distribution. Notationally, sometimes we write it like this. Now the PDF, the probability density function, is given by this equation over here. So if you know what the mean is and you know what sigma is, right, then if this function, right, so suppose that this is a good approximation for the data, then we can estimate probabilities by integrating, right, this f of x over the relevant ranges that we want to do, right? So that's the basic idea. So obviously we're not going to be doing the integrations, but right, we'll be using computer software to help us calculate all these integrations and probabilities. But that's the underlying idea, right, with probability density functions, right, using the areas under the probability density functions to find proportions. A very special kind of normal distribution, so if it has mean 0 and standard deviation 1, it's called a standard normal distribution. Now it turns out that any normal distribution, whatever its mean and standard deviation, any normal distribution can be standardized by the following equation, right? So if you subtract the mean from the normal distribution and divide it by sigma, this variable z will then follow what we call a standard normal distribution. There's some other terminology over here. Some people call these z-scores or standardized scores. Those are equivalent terminology that people have to talk about these the standard normal distribution, right? Right, so we'll say the z-scores follow a normal distribution, standard normal distribution, standardized scores follow a normal distribution.